Einstein's theory of special relativity is familiar to most of us, but general relativity has always been a bit more obscure. Now, for years I heard, it is so complicated, the math is just unbelievable. So I thought it was something really exotic that I would just never have the patience to wade through. But I finally took a look at it and found it's just derivatives. It's like a boatload of derivatives, so it's kind of overwhelming, but each step in the process is actually pretty simple. We do it all the time. So I'm making this video mostly for my engineering friends because you folks know derivatives like the back of your hand. I think it can be easy for you to understand what physicists are doing with Einstein's work. Okay, let's look at the field equations to start with. This is a set of 16 differential equations for the elements of the metric tensor. Okay, you see the indices mu and nu. Each one goes from 0 to 3, so you have 4 times 4, 16 equations. The Schwarzschild solution is the simplest one. That's for a black hole that has no rotation and no charge. We assume a point mass at the origin, and this is something that Schwarzschild did in 1915. Also, in a recent book called the General Relativity Coursebook, Ed Dahl put all the details in. I'll put the references in the description below. Now here's what the solution for the black hole looks like. The metric tensor has 16 components, of course. Most of them are 0. The off-diagonal terms will be non-zero for a rotating black hole, but that is definitely more complicated. The r squared and r squared sine squared theta should be familiar to you from ordinary spherical coordinates that you use in 3 dimensions. There's only two things that we're solving for, the G00 and G11. So you might think this wouldn't be too hard, but somehow when you expand it all out, yeah, there are a lot of terms. Okay, now the metric tensor in relativity is what tells us the space-time interval between 2 events. It's kind of like a distance in 3 dimensions. In special relativity, we use the Minkowski metric. In Cartesian coordinates, it looks like this. And then in spherical coordinates, it looks like this. Going back to the field equations, we see that we know one term, the G mu nu. Now for the simplest problems, such as a black hole, we have empty space, a vacuum. And so the T mu nu terms on the right are all 0. That helps a lot in making it simplified. So what we need to look at is that first term, r mu nu. And this is where it gets very complicated because each of those 16 terms can be expanded 3 times into a lot more terms. It's called the Ricci tensor. And each term of the Ricci tensor is a sum of terms of the Riemann tensor. So then, of course, we need to know what the Riemann tensor is. Well, each term of the Riemann tensor is the sum of terms that involves this gamma symbol, which is called the Christoffel symbol. Now, author Leonard Susskind said that Christoffel symbols are sometimes pronounced Christ awful because people get so tired of calculating so many derivatives. But they're not really that weird. They're also used in just changing coordinates from Cartesian to spherical coordinates in ordinary 3-dimensional space. So you can find them in a standard math textbook, like the one I used in graduate school was by George Arfken. And it tells you all about why the Christoffel symbols are what they are and how you use them. So now in principle, we know how to calculate that Ricci tensor from derivatives, just by plugging in the crystal symbols into the Riemann tensor, then the Riemann components into the equation for the Ricci tensor. There's only one thing left, and that is the Ricci scalar. And as you might expect, it's the sum of terms of the Ricci tensor. So now we actually have all the terms. To solve the equation, we use the standard method. We assume a solution, and then just start taking derivatives of it. Here we see the non-zero terms of the metric, and we just calculate all those derivatives and plug them into the field equation. And here's the solution. The Schwarzschild radius is an integration constant evaluated from the boundary conditions. That tells you the location of the event horizon around the black hole. So what have we done? Derivatives show us how something changes when we move from one point to another. With spherical coordinates, first of all, the basis vectors change from one point to another. So that gives us a lot of derivatives to deal with. And then gravity curves space-time. So what we calculate is how the metric changes from one point to another. We calculated the metric for the simplest black hole. Now the good news is there are software packages available that are specific for relativity calculations, so we don't have to reinvent the wheel and go through all these calculations all the time. I hope this gives you some insight into what general relativity is about, and thank you for watching.